So, in the 1970s, Hawking found that if one applies the principles of quantum mechanics to objects called black holes, then it turns out that an isolated black hole will not remain black, but rather will start emitting particles. So, these particles are primarily photons and gravitons, but depending on the temperature of the black hole might also be other kinds of particles. So, this is called Hawking radiation, and one intuitive way to understand how it emerges is that in quantum mechanics everything fluctuates, including what we think of as the vacuum. So, when there are fluctuations of the vacuum near the horizon of the black hole, such fluctuations can sometimes produce pairs of particles, okay, which are produced for some time and then annihilate and go back into the vacuum. But in such a process, it might happen that one of particle out of this pair comes out of the black hole, whereas the other one falls into the black hole. So, if you have an observer who is observing the black hole from a distance, it would appear as if there was a steady stream of particles that was emerging from the black hole. The reason this is compared with black body radiation is that the spectrum that is produced by the black hole is exactly that of a black body. By that, I mean that when one considers a black body radiates at a temperature, at a frequency which is controlled by the temperature of the black body. So, a hotter black body would tend to radiate more blue light, whereas a cooler black body would tend to radiate more red light. But a black body still, even at a given temperature, radiates photons of many different frequencies. And there is a particular ratio of how much energy is radiated at a given frequency to how much energy is radiated at a different frequency. And this is also the ratio that is maintained by the black hole in its radiation, and that's why black hole radiation is called black body radiation. So, when Hawking discovered this process of Hawking radiation, he also found an additional property of Hawking radiation, which is that the radiation that is emitted from a black hole, Hawking argued, was completely independent of what constituted the black hole in the first place. So, black holes can be constituted by different processes. Different kinds of stars might collapse to form a black hole. Maybe one star has more hydrogen, maybe the other star has less hydrogen, it has more carbon. But Hawking found that regardless of these initial conditions, the Hawking radiation that would be produced would be the same in all cases and would only depend on the mass and charge and angular momentum of the black hole and on nothing else. Now, if one therefore imagines some black hole that is just allowed to evaporate away entirely, then Hawking argued that the final state, which would just be some radiation that was produced by the black hole because there's no black hole anymore, would be independent of the initial process that led to the formation of the black hole. Now, this kind of a process where you find a final state that's independent of the initial state is in conflict with what we know about physics from many other experiments and settings. So, we have always found from the time of classical physics, now 400 years ago, that in physics, time evolution can always be reversed. If you give me the final state of a process, I can also calculate its initial state. So, if I have a cannonball and I shoot it with some velocity, I can calculate where it will end up. But if you tell me at an intermediate time what the position and velocity is, I can also calculate where it came from. So, Hawking argued that this principle of reversibility of time evolution would be violated by black holes. And this principle of reversibility of time evolution is obtained in its most evolved form in the modern theory of quantum mechanics, where it is called the principle of unitarity. The principle of unitarity basically simply says that if you look at the state of a system, the evolution of this system in time is such that there's always an exactly one-to-one map between the state at a later time and the state at an earlier time. So, if you give me the state at any time, I can predict the future of the system, but also its past. And Hawking argued that this would be violated by black holes. and this therefore would lead to some kind of potential contradiction between the theory of gravity which Hawking used to perform his calculations and the principles of quantum mechanics. And this is very briefly put what the black hole information paradox is. So the reason this paradox is called the information paradox here, information is not being used in a very technical sense. It simply means that a black hole tends to lose information in that it acts as a perfect shredder. So as I said, black holes could be formed out of stars of different kinds. But if the final radiation that is produced by the black hole does not have information about the initial state of the black hole, this means that some information has been lost. Okay, so to put it in a more dramatic manner, one could take a black hole that had been formed and one could throw a copy of the encyclopedia into it, a copy of Wikipedia into it. And if one did that, if the radiation that was produced was still independent of the details of what fell in, then that means that the information that we threw into the black hole would be irreversibly lost. So here information is just used to refer to the fact that the initial state of the black hole and what all went into constituting the black hole cannot be reconstructed from the final state of black hole evaporation. And so this is called the information paradox because it suggests that information is being lost in the process of black hole evaporation. Whereas, as I explained earlier, everything we know from every experiment that we have done in other aspects of physics tells us that information is never lost in time evolution. Information is not lost in any other physical process, and that's why it's called the information paradox. Hawking's argument was that the initial state that constituted the black hole has a lot of information if you use information in the sense that I explained, in that the composition of the star that constituted the black hole could have been different. The star could have had many other features on its surface, could have had some other distribution of density. All that is what is called information about the initial state. But Hawking argued that the final radiation that would emerge would only depend on the total mass and the charge and the angular momentum of the star, which is some information, but it's far from all the information that was present in the initial state of the star. And so that Hawking's argument was that information would be lost in black hole evaporation. So this is a good question because usually one might think that one sees processes that are irreversible all around us. If one burns a piece of paper, it looks like the information on the piece of paper has been lost. But in fact, we understand that if one keeps track very carefully of the microscopic details of the light and the smoke that was produced by burning the piece of paper and everything else that was affected around it, then in principle, we could reconstruct everything that went into the paper in the first place. We could reconstruct what was written in the paper in the first place. This is something very hard to do in practice, but nevertheless, in all aspects of physics, in simpler experiments, we can always reconstruct what the initial state of a system was. Similarly, there is no such thing as a perfect shredder. A shredder could tear up a piece of paper into many different parts, but with enough effort, one can always put them back together again. So, a very fundamental principle of physics is that if one keeps track of all the microscopic details of a system to sufficient accuracy, then even though processes might appear to lose information, they do not actually lose information. So the processes that we see around us, these are what are sometimes called dissipative processes that appear to lose information, in fact do not lose information at a microscopic scale. They only appear to lose information at a macroscopic scale. Now what Hawking argued was that black holes would lose information even at a microscopic scale. So Hawking's main point was that even if one kept track of all aspects of Hawking radiation, one made measurements that were as precise as one would like, one would still not be able to recover the initial state of the black hole. So Hawking argued there was a fundamental difference between ordinary blackbody radiation that appears to be dissipative but is not really dissipative at a microscopic level, and the radiation that emerged from black holes that he argued would genuinely lead to the loss of information. If you imagine some arrangement of balls on a snooker table, which is initially very symmetric. Okay? Now, if one goes and disturbs that arrangement, then of course it's very hard to tell at a later stage what the initial arrangement was. But what physics tells us is that if one keeps track of every microscopic detail of the different balls and everything else that was disturbed and how the snooker table was disturbed, then one can in fact back calculate what the initial arrangement was. Okay, so this is it's not only about text and paper, but this is something that's a general principle of physics. That even though it might appear that macroscopically processes are not reversible, in fact, at a microscopic scale, all processes are reversible. So, a lot of progress has been made on understanding quantum aspects of black holes in the 50 years since Hawking proposed the paradox. And the current understanding is that Hawking's argument had subtle errors, and in fact, the principle of unitarity is preserved in the process of black hole evaporation. And it is not the case that black hole evaporation loses information. This requires some corrections to how we perceive space-time and how we understand gravity, but the principle of unitarity is believed to be preserved and can be consistently preserved. So, a lot of research over the past 50 years has gradually persuaded almost all researchers in the field that information is not lost. So, the main contribution which this prize recognizes, which is the main contribution we made in this area, was to point out that information in a theory of quantum gravity is localized in a way that's very different from the way we usually think of information being localized. So, what we pointed out was that usually one thinks of information as being confined to one region. There's some information that's present in the hard disk of your laptop, and that's just confined where it is. And one cannot, probe that information without physically accessing the laptop. So what we pointed out is that when one combines quantum mechanics and gravitational effects, this very familiar, very mundane notion of how information is localized, in fact, changes very dramatically. And what we've shown in work with several collaborators is that a general principle of quantum gravity is that information that is available inside some bounded region, inside some finite region, can in fact be accessed by observers using gravitational effects who are outside that region, so without directly entering that region. So that might seem, like some science fiction idea, but it is in fact something that comes out consistently from our understanding of quantum mechanics and gravity. So in fact, it comes out consistently from a rather conservative putting together of quantum mechanics and gravity. And the reason this is relevant for resolving the information paradox is that it tells us that information that's available inside the black hole is also available outside the black hole. So even as the black hole evaporates away, there is always a complete copy of the information that remains outside, and therefore information is not lost. And that's the way this very interesting and surprising effect that is present in quantum gravity also helps to resolve this old paradox. So Hawking was not aware of this unusual localization of information in gravity. And one of the assumptions that Hawking made was that even in the presence of quantum mechanics and gravity, information would be localized just as we ordinarily think of it being localized. So Hawking assumed that information that was available inside the black hole, or that was present inside the black hole, would not be accessible to an observer outside. In fact, as I described in the beginning, he argued that the only thing that would be available outside would be the mass and charge and total angular momentum of the black hole, but not other details. So Hawking's error was to overlook this unusual localization of information in gravity. I mean, this is something that wasn't understood at the time, but the error in Hawking's argument was to overlook this unusual localization of information. And when one discards the incorrect assumption that information is localized in gravity just as it is in ordinary theories, then one does not arrive at a contradiction anymore. So, of course, there are more technical arguments to prove this, but I'm going to try and give you a very quick and intuitive explanation of why it is hard to localize information in quantum gravity. So, it involves some very basic principles of quantum mechanics and of gravity. Okay. So, the principle of quantum mechanics that I'm going to invoke is called the Heisenberg uncertainty principle, and the principle of gravity that I'll invoke is called the Gauss law. Okay. So, the Heisenberg uncertainty principle tells us that if one has a state which has, or an excitation which has a definite energy, then it cannot be confined to a finite region. Okay. So, the way in a non-gravitational theory one usually confines information to a finite region is by taking a superposition of wave functions. So, in quantum mechanics, as states of matter can be superposed just as states of, just as light waves can be superposed. And in particular, by superposing these states in just the right way, we can arrange for information or for an excitation to be localized in a given region by ensuring that the quantum mechanical wave function interferes destructively outside some region and interferes constructively inside a region. So, this is something one can do with waves on water as well. One can arrange for waves on water in such a way that you get a big peak in one region and you have nothing outside that region. And that's when the waves are interfering constructively inside that region and destructively outside that region. Okay. So, this is what happens in quantum mechanics, and if we just have quantum mechanics without gravity, then one can localize information as one does usually in mundane life. However, when one adds in gravitational effects, then there's an additional effect we need to contend with, which is called the Gauss law. And the Gauss law tells us that the energy of a state can be detected at infinity by measuring the gravitational field. So, the energy of a state can always be detected by looking at some Gaussian surface far away and by integrating the gravitational field on that Gaussian surface. So, in particular, now what happens is that if you try to superpose these quantum mechanical wave functions, each of which has a different energy, one has to contend with the fact that each of these wave functions also has an accompanying gravitational field which extends out to infinity. So, earlier we had these different waves which we wanted to superpose in such a way so as to get an excitation in some region in the middle and have nothing outside it. But now each of these waves has some partner degree of freedom, which is the gravitational field, and that gravitational field is extending out to infinity. And so, what one could do earlier, which is add up these waves so as to make them add up constructively in the middle and destructively outside, one cannot do in the presence of the gravitational field, because the gravitational field is outside and it prevents us from coming up with such an arrangement. And so, by extending this kind of an intuition, we were able to show that if one makes measurements of the gravitational field and of other observables outside some region, one can reconstruct the information inside that region. And so, this is why information is localized unusually in a theory of gravity. It's a combination of quantum mechanics and gravitational effects that's leading to this delocalization of information. So, if one just considers the theory of quantum mechanics, then information is localized in the absence of gravity, much as we think of it in everyday life. And that is because, as I said, one can superpose the quantum mechanical waves of different energies so as to get some localized excitation in some region and destructive interference outside that region. If one thinks of gravitational excitations in the absence of quantum mechanics, then once again we can hide information or localize information. In fact, there are classic theorems in the theory of gravity that tell us that if one considers a spherically symmetric distribution of matter, then the gravitational field outside is sensitive only to the total mass and not to the details of the density distribution inside the matter. And in fact, this is what Hawking assumed in his statement of the paradox. But when one considers both the gravitational field and quantum mechanical effects, then one finds this unusual phenomena where one has these quantum mechanical wave functions that one needs to superpose, but each of these wave functions is dressed in a way with a gravitational field that extends out to infinity. So, what one could do in only quantum mechanics without gravity, or what one could do in only a theory of gravity where one didn't account for quantum mechanical effects, one cannot do in a theory of quantum gravity. So this effect arises as a result of both the Gauss law and the Heisenberg uncertainty principle, and not due to any one of them individually. So there's been a lot of activity recently on the information paradox from a slightly different perspective, which leads to this so-called island proposal. Roughly speaking, this island proposal realizes the intuition that I described earlier, which is that information inside the black hole can be accessed by observations far away. So this is an effect that we had first conjectured in collaboration with my close collaborator Kyriakos Paparodimos, who's at CERN several years ago. And the island proposal realizes an aspect of this proposal that we put forward by stating that there is a region inside the black hole which is called the island, whose information can be accessed from far away. However, the island proposal is not completely consistent with our ideas, and the reason for that is that the island proposal also states that there is a region which is outside the island. You could think of it as a sea outside the island, whose information cannot be obtained from far away. So in fact, we showed with a number of collaborators that this island proposal is not consistent in standard theories of gravity. So the proposals, this proposal works in some slightly modified theories of gravity, where gravity extends out to some finite region and then it just completely switches off beyond that region. And if one considers standard theories of gravity of the kind in our universe, then the island proposal is not the right way to think about black holes, but rather one should recognize that all the information inside a bounded region, not just the information inside some island, but all the information inside a bounded region is available to observers outside. So the holographic principle is a principle about quantum gravity, which is the idea that the dynamics of quantum gravity in some bulk of a space-time can in fact be understood only from its boundary. Now, this principle has been made precise in specific string theoretic models, and most notably was made precise in 1997 through the discovery of what is called the ADS-CFT correspondence. What our work shows, and the way our work relates to this, is that the holographic principle of this is not just a property of specific string theoretic models of gravity, but rather arises due to some very general principles of quantum mechanics and gravity. So any consistent theory of quantum gravity, including the one that should apply to our universe where we don't have a full string theoretic description, should also obey this holographic principle. This is what would lead us to the conclusion that if one looks at black holes, the dynamics and the information that's inside the black hole can be described by some observations that are far away and outside the black hole. So the way our work relates to this principle is roughly by explaining why it is that theories of quantum gravity are holographic. So, in fact, my interest in this subject coincides almost exactly with the time I moved to ICTS, which was now in about 10 years ago, and so this is one of the main themes that has been the focus of my work in ICTS. A lot of my early work was done in collaboration with Kyriakos Paparodimos, who was at CERN, whom I mentioned earlier as well. But I've collaborated with many members at ICTS. Many of my students. My first student here, Sudeep Ghosh, and Pushkal Srivastav, Chandramoli Chaudhary, Joydeep Chakravarti, who's just graduating, ICTS postdocs, Siddharth Prabhu, Victor Godet, who's here. Also, many other collaborators from many other parts of the world. Olga Papadrilaki, who's now a postdoc in Perimeter Institute, was involved in this work. And some of our work on the island proposal was done as a part of a large collaboration involving Andreas Karch at the University of Texas, Lisa Randall at Harvard, Hao Gang at Harvard, Sanjit Shashi, Carlos Perez, Marcos Riojas at the University of Texas. And so I've benefited from many fantastic collaborators and students and postdocs, and of course this is something that we've discussed many hours, spent many hours discussing at ICTS. So I've benefited enormously from all of these collaborations and discussions.